This is 2015 FRQ number 1 in the graphing calculator section. So make sure you have a graphing calculator with you for the problem numbers 1 and 2. Okay. All right, let's start with the first one. It says the rate at which the rainwater flows into a drain pipe is modeled by the function r, where r of t is equal to 20 sine of t squared over 35 cubic feet per hour. So again, this is the rate at which this is happening. So if we want to know the total cubic feet, then we will need to take the integral because this is the rate. So to know the unit, you will then need to take the integral of this. All right. T is measured in hours and it's between 0 to 8 hours. Beautiful. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by d of t equals negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour. So we have two rates here, right? So if we want to know the total cubic feet, we got to deal with these rates in terms of using integrals. All right. For same hour between 0 to 8 hours, there are 30 cubic feet of water in the pipe initially at t equals 0. Beautiful. So start with the first problem. A, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval between 0 to 8 hours? So we want to know how much cubic feet of rainwater flow into the pipe. So it doesn't matter how much we started with. We just want to know in between 0 to 8 hours, how much is flowing in. So the only function we're looking at is r of t, because that's the rate at which the water is flowing in. And we're looking between 0 to 8 hours. So for part A, it is simply finding the integral between 0 to 8 of r of t dt, right? Which is 0 to 8, 20 sine of t squared over 35 dt. All right, so of course we use our calculator. So I'm going to go ahead and grab my calculator. Okay, and remember it's math 9. It's the integral, right? Math 9. All right, and again, if yours is the older version, you just need to remember how to put your format in. This is the newer version. So we start at 0 to 8 hours. R of t, you can't put R of t, you got to put the entire function in there. So the function was 20 sine of t squared, so x squared over 35, parentheses, all right, dx dt, same thing. And I'm going to double check. My mode has to be in radians. So see, mine's in degree right here, right? I want to make sure it's in radians. So I change it back to radians. All right, done. So I press enter, and that is a total of 76.570. Remember, round to 3 decimal places, right? 76.570. So we go back to our FRQ. So 76.570 cubic feet after 8 hours, right? Remember, FRQs are word problems, so you really want to make sure you answer the question, and definitely double check your units and double check whether you're answering what they're asking you. Okay. All right. Next question says, is the amount of water in the pipe increasing or decreasing at t equals 3 hours? Give a reason for your answer. So we know there's water flowing in, there's water flowing out. So then you got to compare those two and say, hey, at this point, do I have more coming in or more going out, right? Because if there's more coming in, then my water is increasing. But if there's more flowing out, then I definitely have the water decreasing, right? So you got to check the rate at which it is coming in at 3 hours. And it's flowing out, so minus the rate at which it is flowing out at 3 hours, right? So let's take our function. So it would be 20 sine of 9 over 35 minus, parentheses, negative 0.04, 3 cubed is 27, plus 0.4 times 3 squared is 9, plus 0.96 times 3, and let's find the final answer here, right? So of course, again, using our calculator, because nobody expects you to do this by hand. So 20 times sine of 9 over 35, that's the rate at which is coming in, flowing out, subtracting parentheses, 0.04. Just double checking my function here. I have to have my problem up here somewhere, 0.04. Oh, sorry, it's negative 0.04. So minus negative 0.04 t cubed, so times 27, we already figured that out, plus 0.4 times 9 plus 0.96 times 3, close your parentheses, enter. We are at negative 3.136. So it is a negative answer, which means that we have more flowing out than more coming in, than the rate coming in. So the amount of water is decreasing. So the rate is, the answer here was negative 0.314. So that means you have more flowing out than more coming in. Therefore, is the rate at which the water is coming in, the amount of water is increasing or decreasing? It is decreasing at t equals 3 hours, right? So you can explain because the rate flowing in is less than the rate flowing out. Okay. All right. Next, part C says, at what time between 0 to 8 hours is the amount of water in the pipe at a minimum? Justify your answer. So first of all, let's figure out how do we find the amount of water in the pipe, right? So the amount of water in the pipe is equal to the total of the water flowing in minus the total of the water flowing out, right? Because, you know, the rate at which the water is coming in, that's a rate at every single second. If you find the total amount that is happening there, the integral of that, that gives you a total amount of water flowing in the 8 hours. And you take the integral of the water draining out, that gives you the total amount of water draining out. So that's what the difference between those two is, the amount that's remaining in the pipe, right? So it's the integral of the rate coming in minus the rate going out, right? So that will give you the full amount. Now we want to find the minimum of this amount, which means I want to find the minimum of this equation, right? Anytime I want to find a minimum or maximum, it is an extrema. So you find the first derivative. That is your hint, right? Extrema. So we need to find a prime, amount prime. So you take the derivative, and when you take the derivative of an integral, it is just the functions subtracting each other, right? Because integral and derivative sort of cancel each other out. So right now you're really just looking at, you know, a r of t minus d of t. So I'm looking for the minimum, right? That's when you set your first derivative equal to 0. So 0 equals r of t minus d of t. So in other words, if you add d of t to the other side or move them around, you're really looking for when r of t equals d of t. That's when you have your maximum or minimum. Now, because we have an endpoint in this problem, we have a beginning time and an end time. We have a t equals 0 and t equals 8. So those are endpoints. So whenever you have a closed interval and you're looking for a maximum minimum, you must check your extrema that you solve for here against those minimum and against those endpoints. So you got to look at when t equals 0, when t equals 8, what is your amount at those times? Because those are your endpoints. And then this equation here will allow us to figure out an extrema in between those two numbers, right? But we don't know whether that is a minimum or a maximum, unless you want to take the second derivative, which in my opinion, that's too much work. In this case, because you have an endpoint, you can just check against those endpoints, right? So now again, you use your calculator, you try to figure out, hey, when is 20 sine of 9 over 35 equal to negative 0.04, not 9, sorry, t or x, right? X squared over, or t squared. It doesn't really matter your variable because you're putting in the calculator. So x cubed plus 0.4 x squared plus 0.96 x. When are those two equal, right? Again, I'm just going to quickly double check. All right, yes, I got my equation correct. Okay, I'm going to go back to my calculator. Oops. Okay, so when are those two equal to each other? So this is actually better if you graph it out, right? If you graph it out, it's a little bit easier to see where the intersections are. So you think for 20 sine of x squared over 35, that's your first equation. Second equation is negative 0.4 x cubed. So x cubed, I like this one. You could use a caret, doesn't really matter, plus 0.4 x squared plus 0.96 x. Okay, so I'm gonna graph this. And again, your calculator, you may have to do a little bit of shifting and figuring out zooming and stuff, but this is your intersection. Where is it intersecting? It's intersecting at x equals 3.2116. So again, this is, well, you want to be as exact as possible. So typically you want to round, but because you're going to use this answer in your integral, you want to keep as many decimals as possible. So I kept as many as I can. All right. So I kept, and I said, x is about 0.327165845. Right. Yeah. I mean, your calculator can store that number. So if you want to, you can use your calculator to store. So this number is 0.32717, roughly there. Okay. So we're going to plug it into our A of t, right? The amount. So in the beginning, initially, how much was there? It tells you initially it has, where am I? 30 cubic feet, right? So that's where we started. So initially we had 30 cubic feet. Okay. And then at 0. Oh, sorry, not 0 0.3 point. Why am I putting 0 point? I apologize. This is 3.27. It's a problem with running between two different screens. Okay, it's 3.27. So at 3.2717 hour, what is the amount now in the pipe, right? So remember, it is the amount in the pipe is, we started with this. We started with 30. Now we're gonna add on 0 to this number, 3.2717 of R of t minus D of t, because R of t is what's coming in, D of t is what's getting out, right? And then same thing here, this is 30 plus 0 to 8 hours. At the end of 8 hours, R of t minus D of t. Okay, and again, you want to use your math 9 function to do this. And again, to save us time, I am going to show you that this will yield you, and please double check my work, 27.9646, and this should yield you 48.54. So again, because you're comparing these numbers, right, these endpoints against this extrema you got, you will see this extrema is the lowest of all of them. So this is truly a minimum in this equation, right? So then you will say, make sure again you answer your question. Oh, I forgot to box my answer here. That the water is at a minimum when t equals 3.272 hours. Remember, in AP test, we want to round to 3 decimal places. Okay. All right. So that would be my answer for part C. And last but not least, part D. The pipe can hold 50 cubic feet of water before overflowing, for T is greater than 8. Water continues to flow into and out of the pipe at a given rate, at the given rate that's given to you, until the pipe begins to overflow. Write, but do not solve, an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Okay. So how much can the pipe hold, or how much is in the pipe? The pipe has 30 plus integral of R of t minus D of t dt, right? Starting at 0 hour. When is this going to happen? It says t equals W at time W, so that's at W, right? And when is it going to overflow? It's going to overflow once you reach over 50 cubic feet. So once this is equal to 50 feet or more, it's going to start overflowing. And that's your setup. Now we'll clean up a bit. I'm not sure if they want you to clean up, but it doesn't hurt to clean up. We can subtract 30 on both sides to make this a little bit cleaner, so that my equation is really, not 50, sorry, I apologize. It's going to be 20 equals the integral of 0 to W, R of t minus D of t dt. Okay, and that's it.